So we're going to work some basic algebraic manipulation problem. This is probably all stuff that you're very comfortable with. So this is just something to reacquaint ourselves coming out of the summer so that we're prepared to do this sort of thing when we get into some higher order physics problems. So we're going to start off with this example problem. We have an equation y equals 2x plus z, and we want to solve for x. And that means that we have to free x on the right side of this equation, right? And remember PEMDAS. So PEMDAS, parentheses, exponents, multiplication to division, and then addition to subtraction, right? And that's kind of our order of operations. Essentially, when we work to free a variable in order to isolate it when it's involved with other variables and constants on one side of an equation, we essentially want to do PEMDAS in the opposite order. So what we will first do is we'll take an x as part of this term right here, 2x, right? So we want to undo everything that's happening to the 2x first, which means we want to get rid of this z that's over on the right side of the equation. So we will subtract z from the right side first. And if we subtract, let me redo that. Let's do this line by line like we would in algebra class. If we subtract z over on the right side, then, if we add z and we subtract z, then z goes away, right? Whatever we do on the right side, we want to do on the left side as well. So we'll rewrite all of this. This is y minus z on the left, and all that we're left with on the right side is just 2x. Right. And then now we have our lone term over on the right side, which is the term that has x in it. Right. So let's just flip this around. I'm going to rewrite. I'm just going to swap what's on what side. And let's put 2x over on the left now, since we generally like the things we're solving for to be on the left. And then we'll have y minus z over on the right side. So we didn't manipulate the equation at all. We just swapped who's on which side. And now we know that we have x over on the left side. And obviously it's being multiplied by 2. So we will divide by 2. And that will get rid of the 2, right? And leave x by itself. Whatever we do on the left side, we want to do on the right side. So if we get x by itself, it should look like this. Y minus z divided by 2. We can write this a number of different ways. We could write this y over 2 minus z over 2. We could write this as 1 over 2 times y minus z. Doesn't really matter how we express this. All that matters is that we have everything other than x on the right side, and then x isolated by itself over on the left side of our equation. Okay, so our example problem, we played around with a generic algebra equation that used x, y, and z, which are some pretty generic variables. However, going forward with our real problems here, we're going to play around with some equations that we will end up using throughout the course of our 2 semesters here with physics. So the first one is one of our equations for a velocity. And so because these are real physics equations, some of the variables might look kind of funky, right? So we've got this v sub x right here, and that stands for velocity in our horizontal direction. And then we have another v sub x right here, but it's v sub x with a 0 next to it. And we read this as v sub x naught. And this is our initial horizontal velocity, meaning our initial velocity in the horizontal direction. So that's not super key. We're going to talk about this equation pretty early on when we start working on physics proper, but I just wanted to highlight that. And so some of these will look kind of similar, some of these variables, but they're obviously no variable is going to be the exact same as another one, as long as they're 2 distinct variables. And we're just going to manipulate them just like we would any other variable in algebra. So in this equation that we're starting with here, we want to isolate for t. So we, again, want to take this term that has t in it already, and we want to get rid of everything else on that side of the equation, right? Which is the only other thing on that side of the equation is the v sub x naught variable. So we're going to subtract that from the right side. Whatever we subtract on one side, we have to subtract on the other side. Vx naught. So those will go away, right? And we'll be left with vx minus vx naught equals a sub x, or our acceleration in the x direction, times t, which you probably guess is time. And then, of course, we want t by itself, so we will divide the right side by what is multiplying by t at this point in time, which is just a sub x, and then that will get rid of those two. And whatever we do on one side, we got to do on the other side. So we end up with Vx minus Vx naught divided by Ax equals T. And that's our final answer right there. If we wanted to, we can put our variable that we've isolated over on the left side, and it would just look, it would be the same equation, just look slightly different with the t over on the left side rather than on the right side. So either of those are acceptable. Cool. All right, we move on over to question 2, starting with the equation k equals 1/2 m times v squared. We're going to solve for v. And so to solve for v, let's first get rid of this 1/2. To get rid of 1/2, we'll multiply by 2, right? 1/2 times 2 just gets us 1. Whatever we do on one side, we're going to do on the other side. So we end up with 2k equals mv squared. So now we have two variables over on the right side, but no constants. And we will divide by m to get v by itself. So we end up with v squared equals 2k divided by m. So I'm just going to write the v squared over on the left side, v squared equals, and then write all this stuff over on the right side, 2k over m. And then, so the last thing that's happening with v is it's being squared. So obviously to undo a square, we want to take a square root, and whatever we do on the left side, we also have to do on the right side. So we will rewrite all this as v squared, the square root of v squared equals v, right? So v equals whatever we've got over on the right side, which was the square root of 2 times k divided by m. So there we go. We have all of the relationships between mv and k are preserved, but now we've isolated v, velocity, by itself. And so this is how our equation will look if we isolate v. All right, let's move on to question number 3. We're going to start with the equation x equals x naught plus vx naught times t plus 1/2 times ax times t squared. And we're also given a little bit of extra information. So vx naught equals 0. So let me rewrite all this. X equals x naught plus vx naught t plus 1/2 ax times t squared. And vx naught equals 0, right? So we can rewrite all this. V equals x naught plus vx naught is 0. So I'm going to rewrite this with a 0 here. 0 times t plus 1/2 ax t squared, right? And we know that 0 times anything is going to be 0. So we can just get rid of this whole term right here. What I like to do is just cross it out, and then at the end of that arrow, put a 0. And for some reason, I put slashes through my zeros. It's some sort of a math person thing that I picked up, even though I didn't major in math or anything. So I don't know where I picked that up along the way. But I do that, and I apologize if that's confusing at all. That's just a 0 with a slash through it. It just means it goes to 0. And what I like to do is before, rather than inserting the 0 like I did here, right, I like to just do that as I before I even write out the 0, right? So what I would normally do is not even rewrite this with a 0 substituted in for vx naught. I would just say, I know vx naught is 0, so I'm just going to get rid of that whole term right here. So this whole term just goes away, or goes to 0, as I like to say. So we'll rewrite this as x equals x naught plus 1/2 ax t squared. And again, we're trying to solve for t. So now that we got rid of the term that had the vx naught in it, and we're left with x equals x naught plus 1/2 ax t squared, now we want to start solving for t, right? And again, if we think about PEMDAS, we're going to start from the bottom, actually. We're going to do things in the reverse order. So remember that addition and subtraction go together, and then so do multiplication and division. So we want to start with this term that has t in it, and we want to undo anything that's being added or subtracted to that term, which of course is x naught. So we will subtract from the right side x naught. When we do that, x naught goes away from that right side, and then whatever we do on the right side, we got to do on the left side, right? So we'll end up with x minus x naught equals 1/2 times ax t squared. Great. Now to isolate t, we've got a bunch of things. So we did our addition subtraction. There's nothing else being added or subtracted to that term that has t in it, right? But there are a few things that are either being multiplied or divided by, however you want to treat these operations, right? The first one is the 1/2. Let's pretend that's division, right? So let's say this whole thing is being divided by 2. To divide, if this is all being divided by 2, then we want to multiply all this by 2, right? And in doing so, we would undo that multiplying by 1/2 or that dividing by 2, right? So if multiplied by 2. So that 1/2 goes away. And then, of course, whatever we do on one side, we have to do on the other side. So we'll end up multiplying the left side by 2 since we multiplied the right side by 2. And now, to make things a little bit complicated, I'm just going to swap sides as I write these. So a sub x t squared is all that's left over on that right side. I'm just going to write that on the left side. And then what we now have over on the right side, which I'm rewriting from the left side, I'm going to pull that down over here, is 2 times x minus x naught. And then we still have something, a multiplication or division that's occurring to the t, right? So we still have t squared and it's being multiplied by a sub x. So now we want to divide that side by a sub x to get rid of the a sub x, so they go away. Good. And then whatever we do on the left side, we're going to do on the right side, right? So we end up with t squared equals 2 over a sub x times x minus x naught. Is one way to write that. We could have had the 2 times x minus x naught over on the numerator divided by ax and the denominator, but either way gets us there. And then finally, over on the left side, now we've taken care of the multiplication and division. There's no more multiplication and division occurring to t, but there is an exponentiation, right? So now we're on the e step in PEMDAS, and there is no parentheses. So this would be our final step, right? So the t is being squared, and to undo a squaring, we want to take the square root, right? And if we take the square root on the left side, we got to take the square root on the right side. So I'm going to rewrite all this up here. The square root of t squared leaves us with just t, and that equals the square root of 2 times x minus x naught divided by ax. All right, so next one, we've got this equation we're going to start with, and we're going to solve for v. So we got a bunch of things happening to v. We have L on the left side by itself. It's the variable it's currently being isolated. And then we have R times M times V times sine of theta would all be one thing right there, right? That's a trigonometric operator of sine acting on the angle theta. So we want to isolate V, and again, we're just going to undo PEMDAS, right? So we've got a bunch of things that are happening to velocity, but they're all the same type of thing. They're all multiplication, right? So V right here is being multiplied by R, it's being multiplied by M, and it's being multiplied by sine theta. So we can just get rid of all those in one stroke if we wanted to. We can divide by R and divide by M and divide by sine theta, right? And if we did that, if we take R divided by R, that goes away, and divided by M, that goes away, sine theta divided by sine theta, that goes away, and all we're left with is V, which is exactly what we wanted to be the case in the end anyway. So that leaves us with V, and of course, whatever we do on the right side, we have to do on the left side, so we're also going to divide by RM sine theta on the left side, and I'm just going to rewrite this as V, because that's all that was left over on the right side, equals L divided by Rm sine theta. Clean up that L a little bit. Cool. All right, so that one was nice and easy since the only thing that was occurring to our variable that we were looking to isolate was multiplication. Question 4, we've got W equals FD cosine theta. And again, we've got cosine is an operator, right? So C, O, and S here are not variables. They are the trigonometric operation called cosine. So I'm going to rewrite this as W equals big F, which stands for force. We'll talk about force a lot when we get to unit 2, times D, or distance, and then times cosine theta. And so theta is what we want to free, all right? And again, so if we think back to PEMDAS, remember as addition, subtraction, those get handled together. Multiplication, division, they get handled together, and the exponentiation is handled by itself. And finally, Or firstly, if we're going forward, but finally, if we're going backwards, if we're trying to undo everything happening to a variable, then then finally we would deal with parentheses, okay? And I just say that because this is essentially what's happening here, right? So we don't have any explicit parentheses, but we do have this trigonometric operator that's acting on theta, the cosine of theta. So that really is, I would put that under the category of parentheses when we think about PEMDAS. Even though they're implicit, really what's happening here is that theta is kind of trapped inside of parentheses here, and that parentheses is that trigonometric operator of cosine. So we want to handle that last, right? So we'll deal with the addition subtraction first. And in this case, there is no addition subtraction in this problem, right? So we can just move right through those. Multiplication division next. Is there any multiplication divisioning happening to the term in which there is theta? And there certainly is multiplication division, right? D is multiplying cosine theta, and so is F. So we want to undo those two things. And how we would undo that is we'll divide by F, would get rid of F. And then if we also divide by D, we can get rid of D, right? So then that'll leave us with just cosine theta over on the right side. And then, of course, whatever we do on the right side, we have to do on the left side. So we'll divide the W by F and D as well. And we'll end it with W equals FD over the left side equals cosine theta. And then, so then we've taken care of the multiplication and division. There is no exponentiation, right? Theta isn't to any power. So finally, we'll do with our parentheses. And again, the trigonometric operator has parentheses built into it. So that's kind of like we would handle it with this step, right? So in order to handle that, we would take the inverse cosine, right? So this would be the cosine with a little -1 above it. So if we take the cosine, the inverse cosine of cosine times theta, then cosine would go away. And whatever we do on one side, we got to do on the other. So we would just take the inverse cosine over on the left side as well. And then if we rewrite all this, I'm going to rewrite it with theta, which is all that's left over on the right side. I'm going to write that on the left side, and that equals cosine, inverse cosine, times W divided by FD. And of course, now that there's multiple variables, there's more than one thing being acted on by this trigonometric operator of the inverse cosine. Now we explicitly put those parentheses there, right? So now it becomes obvious that there is a parentheses that's occurring at our cosine, or in this case, our inverse cosine. And so that is our answer, that theta equals the inverse cosine of W divided by FD. All right, last one, number 6. We start with this annoying equation. This is called Bernoulli's equation right here, and we're going to play around with it when we get to Unit 8. And so we got P1 plus rho. This guy is a funky little P. He's actually not the letter P. He's a Greek letter called rho, and it looks like a little oar. And that's why it looks like a P, but it looks like also looks like an oar that you would row with on a boat. So rho G times Y1 plus 1 over 2 rho V1 squared equals P2 plus rho G Y2 plus 1/2 rho V2 squared. And then just to make this as annoying as possible, I'm asking you to solve for V2, which is trapped over here. And that allows us to go through again PEMDAS in reverse, but this is a really unwieldy equation with a lot of terms. So let's start at the bottom of PEMDAS. And again, addition, subtraction will handle together, multiplication, division will handle together, and then exponentiation on its own and parentheses on its own. So we're trying to free the V2, and that's in this term right here, right? So we want to take anything that is being added or subtracted to that term and get rid of it first in our first step, right? So we will do that. So, and what's being added to that term is our P2 and our rho GY2. Right, so we'll subtract both those. Let's subtract P2 from the right side, and let's also subtract rho GY2. When we subtract P2, that gets rid of that original P2 that we had. We subtract the rho GY2, that gets rid of that. And then we're left with the only thing over on the right side that's left over is that final term that has V2 in it, so it's 1/2 rho V2 squared. And then, of course, whatever we do on the left side, or whatever we do on the right side, we're going to do on the left side. So we'll subtract P2 over here as well, and also subtract rho GY2 y2. And so we'll rewrite this. I'm just going to keep all the things, all the terms that are kind of like each other together. So we got p1 minus p2. And then we're going to add to that rho gy1, right, which is this guy. And then we're subtracting from that rho gy2. And then we're also still having in there 1/2 rho v1 squared. And then just to simplify things a little bit more, I'm going to rewrite this. We're going to rewrite this so that the term with v2 is over on the left rather than the right, because ultimately that's where we like to have our isolated variable once we're done with all this. So 1/2 rho v2 squared. And then I'm going to rewrite everything we had over on the right side over here on the left. P1 minus P2 in parentheses plus, and then this guy right here, I'm just going to pull out the common variables, which is rho g, and just simplify the subtraction going on inside of that parentheses, right? Because we have y1 minus y2, but then outside of that, we have rho g. So rho g is common to both these terms, right? The rho g y1 minus rho g y2. So we can just pull those out, and we can leave in the parentheses y1 minus y2. Good. And if you don't believe me, try just expand back out these parentheses and see what you get, and you should end up back with these terms together. And then we're going to add to that 1/2 rho v1 squared. Great. And then obviously we still want v2 by itself. So we're going to take, and now we did our addition subtraction. Now we've got division and multiplication. Again, we can handle these in any order. So let's do the multiplication first. So rho is being multiplied by v2 squared, right? So we're going to divide by rho. If I divide that by rho, and if I divide this side by rho, whatever we do on the left side, I'm going to do on the right side. So what we're going to do is let's rewrite the left side. 1/2 v2 squared is all that's left over there. And then I'm going to rewrite each of these terms separately with a rho in the denominator, and then we'll see if it cancels anything out in the numerator of each of these terms over on the right side, okay? So we've got p1 minus p2, and I'll put the rho down the bottom over there, plus rho g times y1 minus y2 divided by rho, and then plus 1/2. Oops, let me put this in the numerator rather than 1/2 rho v1 squared divided by rho, right? So in this term, we can't really do anything about the rho because there's nothing for it to cancel out. But over on this second term, we can simplify because we have a rho in the numerator and a rho in the denominator, and the same thing over in our third term on the right side, right? So those rows will cancel out. And so when I rewrite this next time, I just won't write those rows. Great. And then, of course, so we handled our multiplication because that rho is multiplying the v2 squared, right? Now we have this division right here of the 1/2. So we have to undo that. And of course, the way to undo a division is just with a multiplication. So we can multiply times 2, and then that cancels out our 1/2, right? And of course, whatever we do on the left side, we have to do on the right side. So we'll multiply that right side by 2 as well. So over on the left side, we'll be left with v2 squared. And that will equal 2 times p1 minus p2 over rho. I'm just going to spread out this. I'm just going to distribute this 2 to everything in the parentheses, right? We'll distribute it out to all those guys. So let's distribute that out. So 2 times p1 minus p2 over rho. And then this second term, we've got 2 times g. And remember, I'm not going to write these rows anymore because over in the second term, the rho on the top cancels out the rho on the bottom. So we got 2g times y1 minus y2. And then finally, over here, we got on the third term, the rows canceled out. And now this 2 multiplied times that half cancels out as well, right? So we have 1/2 times 2 times v1 squared, and then 1/2 and that 2 also cancel out. So we end up getting things a little bit simpler over here, right? And then I did forget an addition sign between those first two terms. So good, everything's still adding over on that right side. And then finally, of course, we want to take the square root of v2 squared in order to get a v2 by itself. Whatever we do on the left side, we have to do on the right side. So we will square root everything over here. And so we end up with the square root of v2 squared is just v2, and that equals the square root of however we want to communicate this. I'm going to say 2 over rho times P1 minus P2 plus 2G times y1 minus y2 in parentheses, and finally plus v1 squared by itself. And remember, I can't use that square root to get rid of the v1 squared because it's part of this larger term underneath all of this parentheses, right? It's part of all of this stuff. So we can't isolate it and then take the square root of that v1 squared because it's not v1 squared by itself. It's part of all the rest of this stuff over on the right side, right? So we would just leave that as is for now. We can't really simplify any further, all right? So as unwieldy as this looks, this is our answer. If we isolate starting with this Bernoulli's equation up here, if we isolate for v2 by itself, v2 is going to equal the square root of 2 over rho times p1 minus p2 in parentheses plus 2g times y1 minus y2 in parentheses plus v1 squared, all under that square root. All right, so part 2 here, we're going to bring in a few different equations, combine them, and then do the same thing that we did in part 1, which was just solve for everything in terms of one single variable, isolate that variable. So it's pretty much the exact same thing that we did in part 1, but now we got to combine a few equations. So we have a couple of extra steps to get there. So using the following equations, we're going to solve for v in terms of n, which means at the end of this, we want v on the left side, and then some stuff times m or plus other stuff over on the right side. So we just want a bunch of stuff with the m over on the right side, and we want the v by itself nice and clean over on the left side. All right, so that's what we're going to do here. And we're going to start off with, it looks like if you take a look at these equations that I gave you over on the left, we have a sigma f, which you probably have come across sigma in math before. This is the Greek letter sigma. Looks like a triangular E. It in math generally stands for the sum of things. This is a sum of f's. So if we have a bunch of f's, we can add them together or subtract them, and we end up with sigma f, the sum of f's. And then we got fg, we got fb, and those are all in this equation right here. So we're going to start with that equation. So I'm going to rewrite that, and then we'll plug in those other formulas in here as we go. So we'll start off with sigma f equals fg minus fb, and then again we've got a bunch of things. All these other equations are just the components of that first formula, and we can substitute all those in, right? So right here, sigma f equals 0. So let's substitute for sigma f. We'll put in 0. And that's going to equal whatever fg is, which we can substitute that in for fg. So fg equals m times g, the two variables m times g. So we'll substitute that in for fg. And finally, for fb, we can make a substitution there, and we have another formula, another equation that gives us a substitution for fb, and that equals rho times v times g. Cool. All right, so now let's just rewrite this. I'm going to rewrite this without the, I should have originally put things into parentheses, or rewrite it without the parentheses, and we're going to pull any common terms out of each, or any common variables out of the terms over on the right, okay? So we've got 0 is going to equal, and we've got m times g, minus rho times v times g. Another way we can write this, right, is if we pull the g out, g times m minus rho v. So let's rewrite all this as 0 equals g times m minus rho v. And just like we did in part 1, now we want to isolate v, because again, we want to solve for v, so we want v to be by itself. So first, we'll tackle what's happening to v, right? And it looks like this whole thing that's inside the parentheses here is being multiplied by g. So let's get rid of g first. We're going to divide by g, and that g goes away. And then now all the terms in the parentheses, we're going to get rid of the g all at once. And then if we divide the left side by g, that's going to be nice and easy, because 0 divided by g, 0 divided by anything is just going to be 0, right? So I'm going to rewrite the right side over on the left side. We get m minus rho v equals, and then 0 divided by g is just 0. Cool. And then again, we want to get v by itself. So let's tackle whatever is happening to the term that has v in it. So I'm going to subtract out the m. If we subtract out m, then m goes away. Whatever we do on the left side, we're going to do on the right side. So we end up with a negative. We can't forget about that negative, okay? That negative doesn't go away. So we have negative rho v equals negative m. And so the first thing we can do is we multiply each side by -1, and that gets rid of those respective negatives, right? And so -1 times negative rho v, we just make everything positive. Negative m times -1 can make everything positive. And then finally, we've got a v. Sorry. And finally, we got to get rid of everything that's being that is associated with this v, right? So if we simplify, we get rho v equals m by itself. If we divide the left side by rho and the right side by rho, then we cancel out those rows. We end up with v by itself. And so that gives us v equals m divided by rho. And so that is our answer. You'll see we start with 4 different equations over here, right? And to simplify them, we combine them. And then things got pretty simple, especially since one of them was already 0, one of those terms in our original equation, right? So, and then we just solved for a v, right? Which means that v is by itself. And we solved for it in terms of m, which just means that m we find on the right side, and then any other variables or constants that are occurring within this relationship between m and v, they take place over on the right side with m, leaving v by itself over on the left side. So let's do the same thing with question number 2. So we want to solve for v in terms of m. So we've got our 2 equations right here, and we'll notice that a sub c is present in both of them, and so we can kind of substitute into that first equation. We can make a nice clean substitution of this v squared over r for a sub c in that first equation. So we've got f sub c equals m times a sub c, and then I'm going to rewrite this f sub c equals m times, and then since a sub c equals v squared over r, I can substitute that in for AC, right? I can substitute in v squared over r. So if we rewrite this, f sub c equals m times v squared divided by r. And so we want to solve for v in terms of m. So right now we've got v and m are both over on the right side, and neither of them are on the left side. So ultimately we want v on the left side by itself, and then m and all the other stuff over on the right side. So let's start getting rid of everything that's going on with v, all right? Because we want to isolate v. So first thing we can do is we know that r is being divided on the right side. So if we take and we multiply by r, that'll cancel out the r in the denominator. Whatever we do on the right side, we got to do on the left side. So now I'm just going to rewrite. I'm just going to flip-flop the sides of this equation. So we got mv squared equals r times f sub c. And then we've got to get rid of that m. So we'll divide the mv squared term by m, and that cancels out the m that is currently multiplying v squared. Whatever we do on the left side, we're going to do on the right side. So we end up with v squared equals r. M was not squared. So that v squared equals r times fc divided by m, or rfc over m. And then finally, we got v squared. We're going to take the square root of that. So we're just going to square root the left side. Whatever, if we do that, we got square root the right side. We end up with v equals the square root of r times fc divided by m. Cool. So we took and combined those 2 equations, and then we reorganized the new equation we made so that v is by itself, and then everything else, including m, is over on the right side. So v equals the square root of r fc over m. Question 3, use the following equations to solve for a in terms of r. So we need a by itself in terms of r. So let's start with this first equation right here. We've got sigma f equals m1 times a. So we know that we want a in the end. We want to keep that. So we'll combine some other equations in there. So the next one we know that delta f equals fg. So we can substitute that in for, sigma f. So sigma f equals fg. So we can substitute fg in for sigma f. So fg equals m1a. And now we also know that our f big G equals big G times m1 times m2 divided by r squared. So we can substitute that in further for that f big G. Right, so we'll take G m1 m2 over r squared equals m1 times a. And so ultimately, we want to solve for a in terms of r. And what's nice and convenient is right now we've got a by itself, almost by itself, and then r over on the left side of the equation. So we're just gonna flip flop this to get a over on the left side. All right. So we'll just swap the sides here. So m1a equals big G m1 m2 over r squared. And then obviously what's happening with the a over on the left side is it's being multiplied by m1. So let's just divide by m1. If we do that on the left side, we want to do it on the right side. So we'll divide by m1. And since m1's in the numerator, that cancels out. And we end up with a by itself over on the left side equals big G times m2 divided by r squared equals our acceleration in terms of r. Great. So that is our answer there. All right, and last one. This one looks a little bit more complicated than some of the other ones we've come across so far. Use the following equations to solve for k in terms of a. All right, so we've got three equations. We got t equals 2 pi times the square root of m over k. We've got t equals 1 over f. And then we've got x equals a times cosine of 2 pi ft. So we got to figure out some way to combine all of these things, right? And so probably what might be useful to note is we want to take a look, we want to see what terms are common in all of them, right? So this guy's got an F on our equation C down here, and so does equation B, right? And then equation B has a T, and so does equation A. So that's how these guys all link together, right? And there are no other variables that are common across the three equations. So we're going to end up with combining these guys. Equation B will kind of be an intermediary between equations A and equation C. All right. So since we want to get everything in terms of K, we're going to get A in terms of K. We know that K is in here. Let's start with equation C since we got big A there. So X equals big A times cosine of, inside parentheses, 2 pi times F times little t. All right. And so we've got an F, which stands for frequency. Sorry, so I want to say it as frequency accidentally. So F is right here, and we know that there's a relationship between F and big T. So I'm just going to restart with that equation. So big T equals 1 over F. Let's get F into the numerator, because then we can just substitute it in right there for the little f in our equation C. So if we multiply times f on each side, then we end up with f times big T equals, there's f in the numerator and the denominator over there, equals 1. And then we just want to divide by big T. And so this is telling us that our frequency, or f, equals 1 over t, right? Which is very similar to this equation we start out with, right? This is just saying that t is the inverse of f, and then obviously, so f would also be the inverse of t, right? So we can then plug that in for f over here, right? So let's rewrite this equation. X equals big A times cosine times 2 pi. And now I'm going to substitute this in for f, since f is right here. So 1 over big T. And then we still have times little t. All right, great. And then finally, we've got this equation right here. Big T equals 2 pi times the square root of m over k. So let's first rewrite what's happening with our main equation we've been working with. So x equals big A times cosine. And then inside this parentheses, I'm going to write a numerator and a denominator. So 2 pi and little t are still on top, and then divided by the big T is on the bottom, right? So now that we've got all that kind of separated into a numerator and a denominator, let's substitute in what we have for big T. So we can make big T, and I'm kind of going to rewrite it. Says down in the bottom of that denominator. So we'll rewrite this whole thing. X equals big A times cosine times 2 pi times little t is still what's going on top, but then down the bottom, we're going to substitute in all this stuff that t equals, right? So we got t on the bottom. So we'll substitute in for that 2 pi times the square root of m over k, which again is just what t equaled in that equation A over there, right? So we substitute that in for big T. Cool. And then we'll close up that parentheses. And then we can start canceling some things out, right? So it looks like 2 pi's on the top, the numerator, and on the bottom, the denominator, and on that term that's inside the cosine. So let's clean that up a little bit. So we get A times cosine, and all that's left on top is little t divided by the square root of m over k. Now, square roots we can take and we can invert in much a similar way that we would do just normal normal fractions, right? So x equals, I'm just going to rewrite all this, big A times cosine, and then I'm just going to put little t by itself, and then times, this is 1 over square root of m over k, right? But we can just rewrite this as a times cosine times t times the square root of the inverse of what's inside that parenthesis, or inside that square root, right? So the inverse would be k over m under that square root. So this equals big A times cosine of t times square root of k over m. And ultimately, we want to solve for k. So now we want to start from here. Woo! So let's rewrite all this over here. So x equals big A times cosine times t square root of k over m. Okay, and then we're settling for a long haul, all right? So now we got a few different steps here. We got to isolate k by itself, but a lot is happening with k, right? So what we're first going to do is let's get rid of everything outside the cosine, all right? So let's divide by a over on the right side, and whatever we do on the right side, we're going to do on the left side. So that will leave us with x over a equals, the a's canceled out on the right side. So we have cosine times t times square root of k over m. All right, so next up, let's get rid of that cosine, right? So everything that's going on with k is inside that cosine. So we got to take the inverse cosine of the cosine times t times cosine of t times square root of k over m. And that inverse cosine will undo that cosine. Whatever we do on the right side, we're going to do on the left side. So take the inverse cosine of x over a. And then I'm just going to crisscross these. We're going to rewrite whatever's on the right, which is t times the square root of k over m over on the left. And then I'm going to rewrite what was on the left, which was cosine, inverse cosine of x over a over on the right. All right, cool. And then we're gonna refresh a little bit. We'll make a little more space. We're going to lasso this, and let's replace it up over here. So we got t times the square root of k over m equals the inverse cosine of x over a. So now again, our goal is to be freeing k, right? So we got to get undo everything that's happening to k. So right now, outside of that square root that the k is trapped under is the t. So let's get rid of that t. So let's divide left side by t. If we divide the left side by t, we got to divide the right side by t. And over on the left side, our t in the numerator cancels out with our t in the denominator. So now we have the square root of k over m equals the inverse of cosine x over a times 1 over t. A. Great. All right, next up, we got to square everything. Okay, so we'll take what's over on the left. We're going to square it. We'll take what's over on the right. We're going to square it. When we square the square root of k over m, we're left with just k over m by itself. And that's going to equal 1 over t. So 1 over t squared. Oh my God, I can't write that. 1 over t squared. And times the cosine, the inverse cosine of x over a. or just square that. Right, so everything over on the right side is squared. And then finally, last thing, of course, is k is still being divided by m over on the left. So we're going to we're going to multiply by m over on the left, and then we're going to multiply by m over on the right. And so we're left with k equals, I'm going to put m in the numerator, divided by t squared times the inverse cosine of x over a squared. So that was a long haul. You'll see why I saved that for the very last question. But if you are keeping track of all the steps that you do, making sure you do everything on the left and the right, synchronized, and so that you end up with k by itself and then everything else in terms of m over on the right side, or whatever we were supposed to, in terms of a over on the right side. Woo. Doesn't really matter. Just everything else is over on the right side. Then you should be good to go. All right. So if you got lost in any of the steps, just feel free to backtrack to the point where you got lost, and then move forward from there. And of course, if you got any questions, just ask me. All right. So I hope that that review of algebra went well. Obviously, just algebraic manipulation should be relatively easy in its shortest form. And then eventually in this course, we're going to start combining some equations. And you can see that sometimes they get a little bit gnarly, but often they're pretty easy to work with. And we're going to build up from the easier to work with, the more compatible equations, to ones that get a little bit gnarlier over time. So you'll become very familiar with manipulating equations and combining them. This was just a short review, and we'll play around with this so much more during the year. All right. So good luck with those questions. If you have any questions, please let me know. And otherwise, we will see you in another video. Thank you.